네, 큰
Welcome.
박수로
My name is
맞아주시기
Dan Vogen,
바랍니다.
and I'm Vice President for Bentley Systems, focused on our transportation solutions. I'm based in Pittsburgh, Pennsylvania in the US, and work with teams and users around the world. I'm really excited to speak with you all today on digital twins, how they're being used in the real world today, along with some of our vision for them. Though as a company we work on all types of infrastructure, I will definitely focus on transportation today: roads, bridges, and rail. Just a quick look at us so you understand some of my perspective and projects that I will highlight. Bentley is a global company with rich domain experience. We are engineering professionals delivering software for planning, engineering, construction, and operations of infrastructure. We've operated in over 90 locations in 41 countries. We have more than 4,000 colleagues globally and conduct work in 68 languages with very significant high levels of education. So what's happening in the real world, and why are digital twins so important? Today, about 55% of the world's population lives in cities, and this number is expected to grow 68% in the next 30 years. That's nearly 7 billion people. This urbanization places a huge strain on our road and rail networks, as they really are the only way to keep our cities moving. We see so many issues around the world with insufficient infrastructure, as well as aging infrastructure, that we just cannot maintain fast enough. Second is the environment we live in. I do not think anyone denies that there is an urgent need to respond to climate change and the damage that we as its current custodians are doing to the planet. Our future has to be more sustainable, and this is already being reflected in government, project, and organizational targets for carbon reduction and neutrality being set. Whether it's through smarter decisions at the decision stage, or at the design stage, use of different materials or methods of construction, or the way we operate our roads and railways, we have to be more sustainable. The decisions we are making today really do matter for tomorrow. We can find many studies about the sources of global carbon emissions and quickly identify areas that can contribute the biggest improvements. We have to address these with great importance as we conduct new designs and construction. The third thing I want to highlight is why we need to work smarter in terms of dealing with the wear and tear on our roads, railways, and in particular bridges. I'm sure that any of us can go and point to countless documents to show how underfunded we are around our transportation infrastructure in general, whether it be a shortfall in funding to address the world's rapidly aging infrastructure, or the shortfalls in revenue that were totally unexpected because of COVID that have affected so much of our operations and planning. Our users are asking for our help, looking to find ways to respond to the pressure they are under to deliver increasing levels of service to internal and/or external stakeholders or to members of the public, to deliver more work for the available budget, and there is always pressure to reduce the time and costs associated with business activity. To reduce risk and liability, these organizations need to ensure compliance with legislation, internal policies and standards, including BIM or carbon reduction, as I mentioned earlier. All three of these are linked by one thing, and that is data, or more importantly, information accessed through data. Timely access to data that organizations can trust is critical. And with the increase in the type, volume, and velocity of data being collected or creating, it is a major driver for the digitalization of business processes in our industry. Let's quickly look at this in a more real-world example. In 2018, the city of Genoa in Italy, indeed the world, saw effects of aging infrastructure with the most tragic of consequences, with the collapse of a 200-meter section of the Morandi Bridge, which killed 43 people and left hundreds homeless. The tragic events of that day also dealt a hammer blow to Italy's proud engineering history, but in just 3 months, Italferry, the consulting and project company of Italian railways, designed a replacement bridge to new safety standards on the same footprint of the previous bridge. Italferry used our BIM technology and a digital twins approach to streamline workflows, and while the loss of life is undoubtedly still very real for everyone affected, rapid engineering and construction returned some of the pride of the nation with the inauguration of the new Polcevera Viaduct. I think it is a reminder to all of us that the safety of those who use our bridges, roads, and railways weighs heavy on the minds of every professional working in the industry. I did a presentation at our Year in Infrastructure conference in 2019 where I joked about 2020 and referred to the number as in one's evaluation at our vision, as in having 2020 or perfect sight. I said we expected great things for our vision and insight. Little did we know how significant COVID could or would impact our understanding, vision, and the priorities for what we all do. I was pointed to this article by Prakash Iyer in Business World. Take some time after this to go look up this bridge in Honduras crossing the Choluteca River. It was opened in 1998 and was an engineering marvel designed to withstand extreme weather conditions. The same year it opened, the area was hit with a hurricane and 75 inches of rain in 4 days. The bridge met the weather challenge, but the adjacent roads washed out. The river actually rerouted, and today there is this incredible bridge over nothing to nowhere. Though we can engineer something really reliable, Mr. Iyer uses this example to remind us that we need to be prepared for change, and we need to adapt to it. We hope with better digital twins, design, simulation, and analytics can improve every aspect of our planning and operation. So with all of this, our advancement to digital twins is more important than ever. From a corporate standpoint, we focus on using engineering, reality, and IoT data as a foundation for what we can visualize. We need to have regular updates and be able to track changes. So we keep an up-to-date twin and not a model of an asset in some previous condition state. And we can then use that current accurate model to perform analyses that allow us to make better decisions. Of course, change in our industry is not a new phenomenon. Around 30 years ago, we went through a similar digital transformation triggered by CAD and hardware advancements, seeing a shift from desktops to servers, to the point where today mobile solutions and the cloud are key elements of most organizations' going digital strategy. Almost in parallel, the way we design, build, and operate our infrastructure has evolved, along with how decisions are made and the outcomes possible. Moving from what we were doing on paper in 2D to CAD, a reliance on drawings and reports to 3D and 4D modeling, which saw BIM standards and processes proven to deliver productivity and quality improvements. More recently, we've seen many of our users further advance techniques using our technology to include 5D, the inclusion of cost and carbon calculations as an integral part of the decision-making process, to the point where today more and more decisions are being made on the data itself. So at Bentley we see, and you will likely have heard us talk about already, digital twins being the next big digital disruption in our industry. It's happening really fast. As you can see here, Bentley's digital twin capabilities are already enabling organizations to visually immerse their teams in the decision-making process, run all manner of analytics to predict and produce different outcomes, and importantly track and manage the constant change we see not just across the delivery of a project, but also through an asset's operational life. Technology enables the convergence of engineering technology and its deliverables, the specs, drawings, models, and analyses during design and construction, with operational technology providing live or near real-time data streams from IoT connected devices or drones, all supported by the appropriate information technology to track change, identify asset types and location, plus maintenance history. That allow us to connect the physical asset in the real world with its digital counterpart, its digital twin. And it's that link, that connectivity, that really makes the difference. What might that look like in practice? Now, in rail, imagine a problem with a canopy on a station. Linked in near real time via an IoT connected sensor, the issue is immediately flagged in the digital twin, allowing the asset manager to access maintenance records or inspections of the physical asset. And with the insight gained, inform the decision-making process during operations, which in turn can allow them to deliver an improved service to the end user, the passengers, or businesses within the station. And all of this comes together to affect the total design, build, operation lifecycle. A digital twin is made up of data from many different repositories. We often talk about ET, IT, and OT. We've also found this ST, or spatial technology, or what we call digital context, is a great way to get started with digital twins. We want to transition from document-driven to data-driven decision-making. Your key documents, drawings, maps, and models are made up of layers of graphics. In a similar way, you can think of a digital twin as being made up of layers of data. This is a representative list of the types of layers which might exist in a typical city digital twin. The layers come together to form the digital twin. Each layer is typically stored in its own repository and managed by a particular department. And each layer updates over time at a frequency that makes sense for that layer. Aerial imagery might update once per year, drone data once per quarter, IoT data once every few minutes. The timeline of change, regardless of frequency, helps us do historical analytics and make future predictions. What does this look like in practice? We have the real physical world. We have tools to help with the overall roadway design and the bridge design, and understanding roadway center lines and linear reference systems. Developing more advanced linear reference systems with multiple center lines where we can better locate and attribute data and events. Where we can inventory assets like bridges, signs, lights, and guardrail. Where we can maintain detailed measurement data such as clearances or pavement condition. And we can bring in point clouds and photogrammetry and interrogate those point clouds, or develop reality meshes that provide a real, accurate definition of the current physical state. We can use that point cloud and imagery data to help with automated asset and condition identification. And we can then use all of that data to do things like move objects through the models and make various safety assessments. You can see here a large, oversized, and overweight vehicle, and the kind of point cloud analysis we can do for it to ensure safe movement. With a digital representation that is continuously surveyed, we can provide insights that were not previously possible. The exact same thing is possible in the rail space. We need to ensure that we can take everything we had from the detailed design, confirm the as-built condition, and bring that data forward into our ongoing operations model. precise measurement and collection of track geometry, rail profile, and ride quality information. Doing this every single foot, we have quickly accumulated a very detailed understanding of the current state of the track and how it has changed over time. We have users collecting as many as 40 billion, that's with a B, measurements every month. We use all that data and try to turn it into actionable information, providing insight into critical actions we must take now, as well as prioritizing mid and longer term maintenance work. We create and maintain an accurate linear representation. And with the linear network, provide the foundation for all asset inventory and allow for network segmentation of all linear assets to perform multi-criteria decision support to develop various scenarios of funding optimization. Knowing where all assets are located is important, and having their attributes, maintenance history, and current condition state is paramount. Our inspection processes allow for complete assessment of each asset, combined with the generation of all documentation required for regulatory compliance. We're taking these inspection processes to a new level now, where with very detailed digital twins, we can perform a level of inspection from anywhere in the world. Paired with our new Microsoft HoloLens technology, we can immerse the inspector in the model and have them interact with it as if they were right there on it. With augmented reality, in-field inspectors can see notes on the physical inspection request overlaid on top of the physical structure. I'll show more about this exciting technology in a minute. We can continue to bring in some more information, such as LiDAR and point cloud data. Add that additional context, allowing capabilities like automated asset identification, as well as moving objects through the model and identifying potential clashes with vegetation and other obstructions. We can use that type of information to aid in improving vegetation and maintenance plans. We see here the kind of point cloud collision analysis that's possible that would show issues with fixed assets or vegetation as we move the locomotive through the model. And with good photogrammatic capture, we can create a reality mesh that gives yet another dimension to our understanding of the infrastructure and surrounding topography. And with photogrammetry and models, we can do automated AI and ML-based condition assessment and start the workflows on corrective next actions. Again, a digital representation, continuously surveyed, that allows us to generate insights. The Center for Digital Built Britain put out extensive information on what we need to do for better infrastructure. They focus on people as the users and connections as what ties everything social, economic, and nature together. Looking at what needs to be prioritized for sustainability, but then wrapping that all up in digitalization and the importance of how we build complete models, real digital twins that allow us to study the users, connections, or interactions, assess the sustainable impacts of various changes, and take the best actions overall. So let's look at a few current examples and talk about where we can take these even further in the future. WSP is working with state departments of transportation in Washington State and Oregon on the replacement of a key interstate bridge over the Columbia River. WSP is supporting the use of a digital twin model through the full program lifecycle, from public outreach with conceptual design, through detailed design, into construction, and eventually for operations and as an asset management tool. From beginning to end, this will be a 20-year process, The technology will obviously change a lot over this time. We're well into the back half of the project now, where all the planning and design is done, where getting it right is so critical, and where communication to the departments, the fabricators, the contractors, and the general public are so important. In the beginning, this was a very paper-based, hard to assemble, hard to understand the full extent, and hard to visualize process. The project went through some initial automation improvements, but now digital twins are being fully embraced, looking to provide the most accurate models and visualization for the project. This will affect not only the initial design and construction, but also the long-term operations. We work to move the entire design and project delivery to not only digital, but digital twin, and then have all of that to hand over to the operations and maintenance side upon initial completion. When we say digital delivery, we don't just mean CAD and PDFs, but rather all the application working synergistically. BIM is not just a 3D model with intelligence. It lays the foundation of a digital twin, which becomes a digital living clone of the project, getting and providing live information the project site. The Interstate Bridge Replacement Digital Twin is comprised of the solution through which the data is surfaced, all the data, simulations, and analytics performed on the data, and the communications that are facilitated through the system, data and analytics. All of this is done through some open source standards. With the Interstate Bridge Replacement Project, every asset type is included and modeled with details on construction and future operation. The project is focused on data mobility, ensuring the digital twin will support everything needed for design, construction, operations, maintenance, and renewal, with the details of each phase shown and fully supported. The open source standards are significant as we expect to work with tools from many vendors, allowing data gathering, changes with detailed change sets, and then visualization. This shows all the different vendors and applications we want to make sure can be part of the overall solution, and how important it is that we have an interoperable data model. We really believe this digital twin approach has huge benefits, including improved collaboration and communication, improved design and construction results, with better data flows resulting in more transparency and accessibility with fewer errors and omissions. We can speed the whole process by eliminating unnecessary drawings and the associated review, end up with higher quality construction, and information that is useful to support long-term, more efficient operations and maintenance. Another area we have lots of active digital twin work going, and where we see huge future, is around bridge inspection. This article addresses the huge issues we have today with bridges around the world aging and becoming less sufficient. It speaks to the importance and scale of bridge inspection work and says we need to adopt new processes to keep up with the demands. It also makes some early acknowledgement that some new processes are resulting in some significant efficiencies. Bridge inspections require lots of creativity and engineering in their own right to happen. They can require very expensive equipment. Very often, they have high safety risks. Based on difficulty getting into the right place and ensuring that every part of the structure has been observed, they can be inaccurate and error prone. We always take different pictures and videos to record conditions, but looking at what really changes between two inspections based on pictures from different distances or angles to a specific area of interest can be ineffective. These inspections can take significant time, especially based on having to constantly reposition the equipment we're using to get access to specific parts of the asset. And all of this adds up to very significant costs, both directly for the actual inspection as well as indirectly to the general public that is often inconvenienced by lane or total road closures. We have developed a better way. With images and videos, we can build a reality mesh of the bridge, and we can navigate and investigate that model via a browser, or more impactful, by immersing ourselves in a life-size version of the bridge through a Microsoft HoloLens. These models can be extremely detailed and can allow inspection of the bridge from anywhere in the world, with multiple people coordinating on the inspection, with the inspection done by people who may not be able to physically navigate around the structure. I'll let this video play for a minute or two so that you can see exactly what's possible with these digital twins, the reality mesh of a bridge like this, and what you're able to see and how you're able to interact with it through the HoloLens. Movement and use of the HoloLens and these models can be very natural. You move your head around, you look at the different parts of the bridge just as you are physically standing there. If you physically move, you walk, it will move your position around that bridge. We also have capability here that's shown with a mini map that allows you to go and teleport or transport yourself to a different position just by moving where the camera is in the miniature version of the model. You can see the detail, the clarity of the structure and what's possible just by observing this model, just about as good as being there physically. Looking down the entire length of the bridge, just turning your head sideways. And should we find something of specific interest, we can go and use tools to measure that feature or to isolate it and make specific conditional notes on it. We'll watch here as we do some specific interrogation of this area. See that section isolated, and then our ability to go and make quick notes or conditional assessments, be able to go back to that specific area very quick and easily through the tools. We can get into automated detection of various conditions, highlight those. There's some areas of cracking that we question here, it's shown in highlights. We can provide precise measurement capabilities and allow the inspector to take detailed notes from that. Here we'll go and place a few points in the model and generate detailed measurements. This reality mesh and immersive inspection process creates a whole new world of possibilities, allowing for more coordination, better understanding of actual change over time, more effective use of the time we actually spend in the field, and augmented reality collaboration and inspection notes when working in the field, where we can take notes in the model and then see those notes specifically overlaid on the physical asset in augmented reality. Here's another example of another structure showing the fine level detail we can get with the models. This looks pretty good in the video, but I have to say it's amazing when you have the HoloLens on and actually immerse yourself on or around the bridge. Again, I'll let this play just for a minute or so here, just so you can hopefully get an appreciation for exactly how detailed, what fine resolution and clarity these models have. Again, all by assembling a few thousand pictures together. You can see as this was done in someone's apartment, do this anywhere in the world. We're working on advanced AI and machine learning to help identify defects or deterioration. When we create the model, we can run it through our detectors and have an initial automated inspection pass through done before the user first looks at the model. That automated pre-inspection may not be perfect, but it can definitely provide an easy method for the inspector to quickly look at initially identified issues. We can use AI to identify issues with pavement and even railroad track. With regular surveying, we use AI to help us predict future condition states, allowing a move from regimented, calendar-based inspections and planning towards more reliability-centered maintenance. Overall, these new inspection processes with digital twins can result in cost savings, improved historical data quality, and reducing risks of missing issues. The models can be used to improve planning the infield work and can greatly improve safety. We see the first early adopters leading the way in using the technology and have been told that as much as 90% of the infield work might be done in the office now based on these processes and the quality of the models being created. Another digital twin example is around rail operation and maintenance. Owner-operators are deploying new measurement and scanning technology, even in full-speed revenue-producing lines to collect track geometry, rail profile, LiDAR, and photogrammetry. Canadian National has seen improvement in safety and reliability while reducing costs and creating more network capacity. In this kind of solution, we understand the specific track locations and attributes. We can have three-dimensional reality meshes of any part of the network, and we'll process millions and even billions of measurements each month. We have advanced methods for visualizing all that data, looking at a specific track, understanding the layout of the track, where it's in straight sections, where there are curves, and then looking at the various measurements for geometry, rail profile along these linear sections. We can visualize overall track quality indices, show where maintenance has occurred, and highlight where maintenance should be considered. Here's another view of similar information. We build a digital twin from all this data, logically or digitally representing exactly what is in the field. We can perform analyses and simulations, look for various patterns, identify mission-critical situations or gradually changing conditions, and automatically determine the best maintenance strategy to allow for the most effective use of limited operation budgets. You may have seen a recent press release about Bentley and SMRT in Singapore, and this is exactly the technology that's in play there. All of this leverages the 5 V's, taking in a large volume of data, working with more data more frequently from a velocity standpoint, considering the veracity or accuracy of the data, looking for a wide variety of information to build the most complete model possible, and providing the greatest visibility into the specific work at hand. When combined effectively, we can create huge value for our users. One of the most important parts of a digital twin, I think one of the biggest differentiators between a digital twin and BIM, is that it must be continuously surveyed. A model that becomes outdated is not as valuable to us, and depending on how we use it, we might actually arrive at incorrect conclusions. Continuous surveying is critical in ensuring our digital twins enable the most correct insights. We see so many ways this is happening now, with so much more investment being made to allow easier, cheaper, more frequent data collections. The more we install smart equipment, have more sensors in place, and maybe more important, collect data from relatively cheap and extremely more mobile devices, the better we will be. Think about what it took for someone like Google to drive all the streets in an area versus what might be possible if everyone had their smartphone recording specific aspects of their travel. How much more data will we collect? How much sooner might we be able to detect some change, whether to the presence or absence of assets or the condition of those assets? We should expect the 5 V's I mentioned just a couple minutes ago to become so much more important, with the volume and velocity of data continuing at unbelievable pace. Our need to ensure its veracity or accuracy is being a more complicated problem, enabling even greater value for the asset owners, as well as for us in the general public. McKinsey & Company released a report titled How Construction Can Emerge Stronger After Coronavirus, which I'd encourage you to read. Just look at the quote here. Now is the time to start reimagining our industry and how organizations can emerge in the next normal from a position of strength. We have to find a safe, sustainable way of overcoming this and every other challenge we encounter in what is already a very complex industry. In the short term, McKinsey advocate increased digitalization, remote working, and a greater reliance on BIM, advancing it to include 4D and 5D simulation to replan and re-optimize project schedules, but also digital twin solutions that can provide current and ongoing feedback and insight to the decision process. Longer term, they see the case for digital tools proven to increase productivity to become even stronger. Acceleration and automation across the design and construction phases, including increased use of off-site construction, where working in more easily controlled environments makes it easier to keep people safe and drives up quality. I will end with showing summaries of a few more examples of pioneering digital twin implementations. All of these users and projects were recognized through our corporate awards. Network Rail overcame challenges under COVID-19 lockdown with digital twins. New York State Department of Transportation used digital twins for their first full 3D contracted project. And a digital twin shortened the modeling process and provided great ROI in design for Arup and a new city center design in Dublin, Ireland. We have many others that you can go review as well. And with that, I'll thank you for your time. I hope that you see how quickly we are making huge steps forward with digital twins and that there is much more we can do. I'll be happy to answer any questions.